And this problem has to do with these yellow books. I tried to bring one, but I couldn't find one in my house anymore, and we don't even have them anymore. I realized that might be because I'm starting to get a bit older. So who remembers these things? Ah, yes, I'm not old yet. Okay. Phone books. I used to love these things as a kid. Right? You could find anything in there. The number to the local Intertoys, the number to the hairdressers, everything would be in there. Lovely. But perhaps, okay, we need to update this a little bit. Yeah, okay, I really am getting old. But who's been to a library recently? Ah, good. Okay, better than a computer scientist. So in a library, when you're looking for a book, there's one great feature of the library that we can exploit. Namely that the books are sorted. Imagine, for instance, that like me, you're looking to reread To Kill a Mockingbird again, written by Harper Lee. Now, when you get to the shelf of books, the first one you find is this book by David Baldacci. Okay, B is before L, right? They're always sorted by last name. So that means we need to go further down the shelf. So I walk a couple of steps, and then suddenly I notice that I'm now next to the Amber Spyglass, which is written by Philip Pullman. Ah, P, but P is after L. So that means I need to backtrack a bit. Now this idea of searching in a sorted list is something we can formalize a bit. So let's try to do that. And we're going to try and find a better way of searching for a specific item. Remember that we've already seen a way of doing this. We've seen the in operator of Python. That was linear time because it just checked every single element. But now we're in a library where the books are sorted. And we're going to try to exploit this to somehow get to something that's better than linear time. Better than checking all the books. Let's see if we can get there. To get there, we're going to use recursion. Google's great when you Google recursion. So what's recursion again? Well, you should have seen this in your previous course, Introduction to Programming, but let me refresh your memory a little bit. A recursive function is a function that calls itself. And the example that I always choose for that is one for the Fibonacci series. Right? To find the nth Fibonacci number, I just need to add the previous two together. N minus 2, slide 33. So I need to add fn minus 1 plus fn minus 2 together. And I can translate this to Python. If n is smaller than or equal to 2, I'll return 1, because those are the first two Fibonacci numbers. And otherwise, n minus 1 plus n minus 2. A recursive function because it's a function that calls itself. So far, so good? Okay. Then let's formalize our problem of looking for a book in the library. And we'll formalize it like this. Given a sorted list, for now, all I'm interested in is finding out if it contains a certain value. We could also go to find out where exactly the value is, but the code gets a little bit more messy if we do that. So for the idea, let's just go for whether it contains the item or not. So what would such an example look like? Well, something like this. These are the last names of all of the people involved in this course. And I want to know whether it contains Sam. The answer is yes. How do I know? Well, it's right there. I can see it. And I can find out by either checking all of the elements, or perhaps I can do something better. So how can we get there a bit better? And like I said, remember that this is our time to beat. We want to be better than linear time. Okay, let's try to build our algorithm that's going to do this. And the algorithm that we're going to build is called binary search. Have you heard, who's heard of binary search before? Okay, new to most of you. Good, good. So let's try to build it. What do we start with? Well, if I have a certain list and it's sorted, why don't I look at the one in the exact middle? We'll take the exact middle element, and if this happens to be the book we're looking for, great, we're done. So that's all I've written down so far. We take the middle element, this has a certain value x, it's a certain book, and if that's the book that I'm looking for, great, I'm done. But if it's not, well, then I need to continue searching. And this is where my library strategy comes in. Right? If this was the Baldacci book, I had to continue, I had to move forward. If this was the Pullman book, I had to move backwards. So if x is larger than v, then I need to go to some side of the list. And if x is smaller than v, I need to go to some side of the list. Let's see which goes where. Okay, 87% got the right answer. If x is larger than v, that means we found that in the middle, we're already too far. It's already the Pullman book, the book that's further in the shelf than we want. So that means we need to go back. So we need to go back to the left side of the list. If it turns out that this book in the middle is the Baldacci book, then we need to move forward because we're still before the book that we're looking for. So indeed, if x is larger than v, we go to the left, and if x is smaller than v, we start looking in the right side of the list. Question. How do you determine if something is larger? Good question. It depends on the things in the list. So if the list is just integers, we know how to do this. If it's strings, then it depends on the alphabetical order. And I believe, but perhaps Yoshi can correct me if I'm wrong, that Python also supports the larger than operator on strings. We would have to check. But we could compare two strings in some way as well and find out which one becomes before the other one in the alphabet or in a dictionary. So far so good. If the middle one is larger, we go to the left. If it's smaller, we go to the right. And Yoshi has just confirmed that we can compare strings with the larger and smaller than signs. Okay. But we're not done yet, right? This is still a bit too vague. Let's try to be a bit more precise. What happens, for instance, if the list is empty? Well, if the list is empty, it's easy. The book's not going to be in there. So if the list is empty, we return false. Otherwise, we're going to do all of this stuff.